this initial segment, let's look at some alternative systems, particularly for Coulomb's law, and that entails looking a little bit at the electrostatics units in electricity and really magnetism as well. I just say many treatments of electrostatics do not use SI units. That's SI is System International, or it's sometimes called rationalized MKS units. But instead, what they use is an older system of units that actually, in many ways, I prefer and I think is better, and that's the CGS Gaussian units, and I'll detail some of those differences. And you probably have seen some textbooks or papers that were written and use this different notation or different system of units. Uh, in Gaussian units, the electrostatic force law is not expressed in quite the same form. Mhm. Uh, Here in the usual form that you probably were introduced to it in your beginning physics classes and other classes, chemistry classes, is that the electrostatic force, which is in newtons, is got this funny 1 over 4 pi epsilon naught thing in front of it, and where the heck did that thing come from? Uh, and the two charges, this would be the force between the two charges Q and Q prime. I've got them here. These two charges are measured in coulombs, and R is measured in meters. And if you put in the right constant for epsilon naught, then you get a force over here in newtons. And that's the SI or the rationalized MKS units. Okay. However, many people write the electrostatic force in what are called Gaussian units, and that's this form here. They leave off this constant that nobody seems to know exactly where it came from anyway, this 1 over 4 pi epsilon naught. And in addition, they use the centimeter, gram, and seconds as opposed to the meter, kilogram, seconds. And in that system, the charges, I've labeled them not here, the Q and Q prime are in SI units, but here I'll label them, the one charge is Q, but I have to measure it in what are called electrostatic units, or sometimes called stat coulombs, and Q prime likewise in this other system of units. And then the distances are all measured, since it's a CGS system, are all measured in centimeters. And when you do that, you get the force that gets spit out over here, and its units, if you do the units correctly, comes out in dynes, which is the force unit in the CGS system, if you remember. In essence, what the electrostatic system does, the Gaussian system does, is it takes the square root factor, or it takes this 1 over 4 pi epsilon naught, and takes the square root squared and puts a square root under the first Q and a square root of 4 pi epsilon naught under the second Q prime. And that, in essence, then gives you the electrostatic units of charge. It really is related to the SI unit of charge, Q, divided by the square root of 4 pi epsilon naught. When you do that, typically you put all of this in CGS units, and the net result is you get a number over here that's the charge in what are called stat coulombs, or I usually call them ESU, electrostatic units. It's a little shorter to write than stat coulombs. Some people I've seen have used in honor of Benjamin Franklin, who did some electrostatic work. They call them Franklins and abbreviated FR. So that's really old notation, though. But in this particular case, just if you keep your charges in these electrostatic units, then you don't have to carry the 4 pi epsilon naught. And and then the force, provided you use r squared here and the r in centimeters, yeah, you get the force in dynes. And remember, a dyne is 1 gram centimeter per second squared, and it's basically a 10 to the minus fifth newtons. So if you do the unit conversion on it, you can do a similar thing for the electrostatic potential energy. Yeah? And remember, in SI units, it was this, yeah? And that's what we've been using. But in CGS Gaussian, again, you take square root of this squared and put one of the square roots under the first Q and one under the second Q, and you get the charge in electrostatic units, Q and Q prime. These are in electrostatic units. R is in centimeters, and this is a potential energy of interaction, really, in this case, between these two charges. This potential energy is in energy units, which, if you remember in CGS units, those are in ergs. And if you didn't remember, a 1 erg is just a dyne force times a centimeter, and in the unit conversion, it's an energy unit like joule, and 1 erg is 10 to the minus 7 joules. Well, if you do that calculation, uh, if I divide the charge of an electron in coulombs and this constant here, plug in what epsilon naught is, you and turn everything into centimeters and grams, then what you find is that this charge on the electron, 1.6 times 10 to the minus 19th, turns into uh, uh, 4.8 times 10 to the minus 10 electrostatic units. And so, depending on your set of units, you would represent the fundamental charge on the electron always as E. But if you're using SI units, you use 1.6 times 10 to the minus 19th. If you're using these Gaussian units, you would use this value here. And then you don't have to worry about this 1 over 4 pi epsilon naught ever again. Yeah? Now, I have some prejudices in favor of the CGS Gaussian unit that I'm not the only person, but many people would have some prejudice in favor of that CGS Gaussian units. And the SI units, I think, were imposed by a bunch of essentially engineers on the scientific world, and that has come to be known, at least among certain factions of physicists and chemists, as the tyranny of SI. So there was a meeting held back in the late 40s, and they said, hey, all of these units for electricity, we need to have standards here, and so they standardized it. And the only problem was when they chose the units in electricity and magnetism, they got a system of units that came out of this in which the electric field and the magnetic field have totally different sets of units. The electric field has units of volts per meter, and the magnetic field has units of Tesla, and they're totally different. Okay? There's other issues that arise because of this, but the main issue is this, is that long before they met in the late 40s, well, the H.A. Lorentz, Poincaré, Henri Poincaré, and Albert Einstein had developed the system of special relativity, in which they essentially had shown that the electric field and the magnetic field are one physical entity. The electromagnetic field, which is represented by an electromagnetic field tensor, and it creates havoc when you have some components of this tensor having one set of units and another component of it having a different set of units. Yet it's supposed to represent a single physical entity, the electromagnetic field. So they should have the same units, electric and magnetic field, because they're really just looking at different aspects of the same physical entity. Yeah? Well, anyway, we're sort of left with some bad decisions, I think, that took place in the late 40s in this regard to this. Uh, but if you use the CGS Gaussian unit, it releases you from this tyranny of SI units. It's very, very, oh, I don't know, a very problematic thing, I think, if you're writing textbooks and papers. Uh, one of one of the standard textbooks for graduate level electromagnetic theory was by J.D. Jackson out of Cal Berkeley and was used for years and still is used very, very many places for graduate level courses, certainly in physics and other areas. And the first editions of it were put out in CGS Gaussian units. Because he was a good physicist and knew that the electric and magnetic fields should have the same units, and so, uh, but he got lots of pushback, and so in a later edition he switched over to the SI or the rationalized MKS units with the 1 over 4 pi epsilon knots and things in it. And at least for the first half of his textbook. But the second half, when he looked at relativistic phenomena, he had to go back and switch back over to the CGS Gaussian unit. So he succumbed to some degree to the pressure of this, what I call the tyranny of SI units. Well, I'll get off my soapbox on that. For you, the important thing is this. uh, you'll look at read papers in which they will get the electrostatic potential energy between two charges as this, or they'll have the electrostatic potential energy for hydrogen and hydrogenic ions to be of this form here. And you'll say, oh, this, they've made a typo. They've left out the 1 over 4 pi epsilon naught. Well, they probably haven't. I mean, it's possible they could have, but they're just using the CGS Gaussian units or electrostatic units, and for them they take the fundamental charge on the electron as 4.8 times 10 to the minus 10th electrostatic units. They're measuring distances in in centimeters, and the potential energies, and all energies in fact, are coming out in ergs. Although very often they'll rapidly convert those to electron volts, which are important as well in this case. So, well, that's the reason for sometimes you'll see 1 over 4 pi epsilon naught here, and sometimes not.